In this demonstration, we're going to normalize a database. The database is called school, and in that database we are storing a table called enrollment that has information about students, courses, and grades of the students for a particular course. Recall the reasons why we perform normalization. It is for the efficient operation of the database. So when we look at this table, do we see any apparent inefficiencies? Well, unless you have experience in normalizing tables and designing databases, there probably isn't anything apparent to you in this table definition. So let's take a different approach, and instead of looking at the table design, let's look at what data might look like if we chose to use this table design. So let's go look at our database, and here is the enrollment table with sample data. So now immediately you should see that there are issues with the data within this table. For example, student ID number 1, Dana Scully, also is in another course as student ID number 8. However, in this case, somebody misspelled her name when they input it to the database. So we have a student with 2 course records in this enrollment table, but the names are misspelled. This is one of the key issues with normalization, is to resolve data inconsistencies. Also, why do we have this student information repeated in the database to begin with? It's an inefficient use of the storage space within the database to store the student name and the student birthday twice. There's no reason for this. That is what normalization is going to solve for us. Same thing with student ID number 7 and 9. Same student, 2 different names. Where else do we see repetitive data? That's the first sign to look for in a normalization exercise, is look for repeating data. Solve the repeating data and you've taken the giant step in normalizing the database. Look at the course information. The course information is also repetitive. We see chemistry class entered twice, biology class entered twice. This is amazingly inefficient. A small table with 9 rows probably doesn't matter. However, imagine a table with 100 million rows, which is not a large database, and having this level of repetitive data would waste an enormous amount of storage space. So we have 2 candidates now for normalization: the student information and the course information. Let's go see what normalized tables might look like for this data. The first thing that we notice is that we've now have separate tables for the students and the courses data. All of the student information, the student ID, the student name, the student birth date, is in the students table. Likewise with the course information, the course ID, the course number, and the course name are stored separately in a table called courses. So for every student, there will exist one and only one record representing that student in the database, in the students table. Likewise for the courses. For every offered course, there will be one and only one record in the database for that course, and it will be in the courses table. So what kind of relationship do these tables have with one another? A student can sign up for more than one course. So there is a one-to-many relationship with a student and the courses. However, a course can have many students assigned to it. Therefore, there is a many-to-many relationship between the students and the courses. And recall from a previous discussion that to implement the design for a many-to-many relationship, we must use a link table. So we've created a student course link table. This table has a link ID, has the student ID and the course ID, and the rest of the data associated with a particular student and course, namely the grade information. Notice that the student ID in the student course link table is the same student ID from the students table. By definition, because we use the primary key from the students table as a key in the student course link table, within the student course link table, student ID is referred to as a foreign key. Likewise, for the course ID, in the student course link table, we use a course ID to identify the course from the courses table. Course ID is the primary key in the courses table. Therefore, in the student course link table, course ID is a foreign key. To define a foreign key using the MySQL Workbench, we go to the Foreign Key tab. We enter a name for the foreign key. Now, as a convention, we put _FK to identify this identifier as a foreign key. So I've created a foreign key, student ID _FK, that references the students table. Which field does it reference in the students table? It references the student ID field. Likewise with the course ID. The course ID foreign key references the courses table. Which field in the courses table? It references the course ID field. As soon as you define these foreign keys, the MySQL Workbench will automatically generate the necessary relationships between the tables in the ER diagram. Now again, we're not concerned about how to create the tables, the SQL code for creating the tables at this point. We will cover this in the course, but not now. What we're concerned with now is normalizing the tables. So we have now isolated the student data. There will be no repetitive student data. There is nothing in the student table that is dependent on any other data, and likewise in the course table. We've isolated the course data in the courses table, and we've removed all repetitive data, and there is no dependency between the data. Therefore, we can say that this database is normalized. There is an argument for moving the grade data out of the link table, creating a grade table that would remove the redundancy of the grade data as well as the dependency that exists within this table on the grade data. We're not going to do that. We're not going to carry the normalization to that next level. You could do it and it would not be wrong, but in this example, we're not going to take that next step. We are satisfied that the database is now sufficiently normalized to reduce the dependency between the data of the students and the courses, and to reduce the repetitiveness of the data within the database. So let's go look at some sample data and see how this looks now in comparison to our original enrollment table. So recall that this is what the original data looked like stored in the enrollment table. Now we have our course data in the courses table, and each course gets one row, one record in the table identifying that course uniquely. Likewise with the students. Every student gets one record in the table. Every student is uniquely identified by one record in this table so that there are no more repetitive student names or student birth dates. And we can be assured of data consistency for both the courses and the students. So how do we link all this together? Well, here's our link table. So we have a student ID, a course ID, and the grade assigned to that student for that course, and the date of the exam when that grade was recorded. So we have student 1 in course 1 received a letter grade of A with a total grade score of 99 on December 15th, 2012. So how do we know who this is? Well, we go to this course table and we see the course ID was Chemistry 1 and student ID 1 was Dana Scully. So looking at the link table, we can say Dana Scully got an A in Chemistry 101. Likewise, student 2 in Chemistry 101 also got an A. Student 2 in course 2, which is Biology 101, got a B. So this structure, this link table allows us to pull the data from both the student and the course tables and bring them together very efficiently in the link table.